Alright, so we are on our last lesson for Chapter 6, and then we're going to have a quiz for Chapter 6. This is on black holes and extrasolar planets. Extrasolar planets won't be on your quiz, but I highly recommend reading about it because it's quite fascinating. And so first, black holes. We're going to go over some terminology. Alright, first, so what is a black hole? It's a very dense body whose escape velocity, and we've calculated escape velocity. Remember, for Earth it was 11.2 kilometers per second, but the escape velocity from this body is faster than the speed of light. And since you can't go faster than the speed of light, you can't escape. The event horizon is like the point of no return. Okay, we've learned from universal gravitation that force changes the closer you are to the object. So once you get close enough, there's a point where the escape speed becomes the speed of light. So past that point, nothing escapes. And that horizon is called the event horizon. The singularity, when we talk about the black hole singularity, that's the dense center of a black hole. We don't actually know what's going on at the dense center because our two theories of general relativity and quantum mechanics don't work well, but hopefully one day we will. And then the Schwartzschild radius. The Schwartzschild radius is just the distance from the singularity, that dense center, to the event horizon. Okay, so it's pretty much the radius of that sphere that you would see as being black. Okay. So that's really all there is to it. The questions that we're going to do are quite straightforward. What we do is we take the equation for escape velocity, which we derived 2 lessons ago from energies. Right? And we said the escape velocity is the square root of 2gm over r. And what we're going to do is we're going to set the escape velocity equal to c. Well, let's square both sides first. So we'll have c squared equals 2gm over r, where that r, I'll write as a capital R, and we'll call it the Schwarzschild radius. Okay, so you can rearrange and solve for the Schwarzschild radius of a black hole simply by knowing the black hole's mass. The rest are constants, right? Our gravitational constant, and c is our speed of light. Don't know if I've mentioned this before, but we're going to use 3.00 times 10 to the power of 8 meters per second, which is about 7 times around the equator of the Earth per second. Pretty fast. So the first question then, on the back, says determine the Schwarzschild radius and the average density of a black hole formed by the gravitational collapse of a star 4 times the sun's mass. Okay, so to do that, we use the equation I just wrote up there, where we're changing v into c. You sub in all your values, and we get 11.8 kilometers. So when you think about that, like, our sun is massively huge. And something 4 times the mass of our sun, when it becomes a black hole, only 11.8 kilometers. I mean, if you were to shrink the Earth to the size of a penny, it would be a black hole. So the Earth, there's no way to actually do that, but the Earth, if it were somehow shrunk to the size of a penny, it would be a black hole the size of a penny. So black holes need to be incredibly small. But of course, we do have supermassive black holes, which are located at the center of galaxies. In fact, our own sun orbits around the supermassive black hole for the Milky Way. Don't worry, we're in like the suburbs of our galaxy. We're not downtown, so don't worry about it. Okay, part B, density. That's just mass over volume. And for the volume, we're going to use the volume of a sphere, which is 4/3 pi r cubed. For r, we'll use the Schwarzschild radius that we calculated in part A. And we get a density of 1.18 times 10 to the 18 kilograms per meter cubed. So if you remember doing densities in chemistry, you'll realize that's huge. And remember, that's only really the average density. We can't really calculate what the density would be of the singularity. Some people say it's infinite, but we don't know. Okay, part 2, or example 2 on the worksheet, is not going to be on any quiz. It's just a fun thing. I wrote the time dilation equation for a simple black hole, one that's not rotating and it's not charged. We're not going to talk about any complications or anything more complicated than very simple static black hole. But if you wanted to, you can certainly use that equation, plug it in to calculate the time dilation. And if you're curious, 1 hour passing for an observer, for the other, for the scientists on the outpost, it's 0.46 hours. So try it, see if you get that answer. It's fun. The next thing I have that I'm talking about is extrasolar planets. So extrasolar planets are planets that are orbiting a star other than our own. So our star is called Sol, which is where the word solar system came from. But if we go to other planets that are orbiting other stars, we call them extrasolar planets. They're very, very hard to find. I mean, even our own planets are very, very hard to find. I mean, Pluto, which, well, I shouldn't mention Pluto, it's not even a planet. But say Uranus and Neptune, you can't see them with the naked eye. We needed telescopes to find them. So imagine trying to find a planet light years away, maybe hundreds or thousands of light years away, orbiting a star. And you might not even be able to see that star with the naked eye. It's a very challenging thing to do. So we have 2 methods actually that I go over. One's called the transit method and the other called the wobble method. I'll just briefly explain them and I'll let you read about them. And I'll also put a video on there as well. There's a good black hole video by Vsauce, and there's a good extrasolar planet video by Acapella Science that I like. So the wobble method is simple. If you have the Earth and it orbits the Sun, okay, the Sun pulls on the Earth, but the Earth also pulls on the Sun. Same with all the other planets. And so the Sun doesn't just sit there in one spot. No, it wobbles as the planets orbit. Right? The planets pull on the Sun as well. Okay, and what we do is we look for that wobble. How do you look for the wobble? Well, we look at the Doppler effect. If you remember the Doppler effect from grade 11, we talked about the Doppler effect with sound, right? Where if an ambulance is coming towards you, the pitch or frequency sounds higher. When it's moving away from you, it sounds lower. Well, the same thing occurs with light. If a star is moving slightly towards you, right, well, its frequency will be slightly blue shifted. Right? It becomes higher. And if it moves away from you, slightly red shifted or lower. So we look at the emission spectra from that star, and we see if it's been blue shifted or red shifted, and we look for a periodic wobble between that blue and red shift. Okay. The other method is the transit method. Now this only works if a planet actually comes in between our point of view and its star, just like that. If it does something like this, then we won't see it. So it has to be on the same plane. But what happens is, when a planet goes in front of its star, it blocks out some of the light. And you see sort of a dip in light intensity. And so we look for that periodic dip in light intensity. And then we can determine planet's mass and how far away from the star it is. What we want to find is a planet around the mass of Earth that's in the Goldilocks zone. So the Goldilocks zone is a place in orbit around its sun that's warm enough to create liquid water, but not hot enough so that water vaporizes. Okay, so call it the Goldilocks zone because we don't want it not too cold, not too hot, just right to have liquid water. Okay, why do we want liquid water? Because as far as we know, that's what is required for life. And that certainly is an interesting question that we've been asking for a very long time. Is there life out there? All right, so that's it for that lesson. And if you have any questions, let me know. Definitely watch those other videos that I'll link for.